In section 3.3, we learn how to write correct formulas for ionic compounds and also use formulas to identify whether a compound is an ionic compound or not. When we write the formulas of ionic compounds, we indicate the number of each ion by a subscript following the formula of the ion. For example, the formula MgCl2 is indicating that we have an ionic compound containing magnesium 2+ ions and Cl- ions in a 1:2 ratio. That is, that there is one magnesium ion for every 2 chloride ions. As you can see, if no subscript is given, it's understood that there is one of that ion present. For example, in the compound magnesium chloride, there is one magnesium ion. In the compound sodium chloride, there is one sodium ion and one chloride ion. And similarly, in the compound potassium bromide, there is one potassium ion and one bromide ion. When we write the formula for an ionic compound, it's important to recognize that we always write the ratio expressed as the set of lowest possible whole numbers. So rather than writing something like Na2Cl2, we'll divide both our subscripts by 2, and we'll just write the compound as NaCl. If you recall from section 2.2, when we were talking about the atomic theory, we noted that some compounds are composed of combinations of electrically charged particles called ions. That is, ionic compounds exist as crystals in which we have a repeating pattern of cations and anions. That is, in ionic compounds, no molecules exist. The formula that we write represents the formula unit, which is the smallest whole number ratio of ions that results in no electrical charge. So in the case of sodium chloride, that would be one sodium ion combining with one chloride ion to form electrically neutral sodium chloride. So back to section 3.3, we want to recognize that electron loss always equals electron gain in an electron transfer process. So if we begin with a neutral set of atoms, after electron transfer, we must end up with an electrically neutral ionic compound. That is, positive and negative ions will always combine in a ratio that gives us electrical neutrality. The difficulty for us is that we need to figure out a reliable method for determining this ratio. Perhaps the easiest way to do this is to use the crossover method, where the charge on one ion becomes the subscript on the other. So for example, when sodium ions combine with oxide ions, the fact that the charge on sodium is +1 tells me that in my formula I will need 1 oxygen, and the fact that the charge on oxygen is 2- tells me that in my formula I will need 2 sodiums. When we do write the formula for an ionic compound, keep in mind that we always want the metal to be on the left and the non-metal on the right, the same as the order of the elements in the periodic table. When we write the formula for an ionic compound, we should always indicate the simplest ratio of anions to cations. And it's important to recognize that sometimes the crossover method doesn't give us this directly. In fact, it might be necessary to divide the result of the crossover method by a whole number to get the correct formula unit. For example, if Pb4+ combined with O2-, we might conclude that we'd need 2 leads and 4 oxygens. However, hopefully you can see that this is not the simplest whole number ratio of lead to oxygen in this compound, and that what we need to do is to divide both of our subscripts by 2 in order to obtain that simplest whole number ratio, which is the correct way of writing the formula of this compound. Now, something that can also help shortcut things is to recognize that if our cation and anion have equal but opposite charges, then they'll always combine in a 1-to-1 ratio. So we can see that magnesium has a 2+ charge, oxygen has a 2- charge. So when they combine, they're going to come together 1-to-1. This saves the need of going through the crossover method and then reducing down. So equal and opposite charges, they always combine 1-to-1. If they don't have equal and opposite charges, use the crossover method, but double check to see if you need to simplify. So this is an exercise from the book. It says write the chemical formula for an ionic compound composed of each pair of ions. So in the first example, it says the calcium ion and the oxygen ion, and we have no charges. But calcium is in group 2A, which means it's going to have a charge of 2+. So calcium 2+ can be combining with the oxygen ion. Oxygen is over in group 6A, so that means that it will have a charge of 2-. And so we can see that these guys have equal and opposite charges, so that means they're going to combine in a 1-to-1 ratio. So that will be CaO. B is a little easier. It says the 2+ copper ion, so Cu indicates copper, put the metal first, and the sulfur ion. And sulfur is also in the 2- column, so that's going to be S2-. And again, we can see that these guys have equal and opposite charges, so they're going to combine 1-to-1. In the next example, we're told that the copper ion has a charge of +1, and it's combining with the sulfur ion, which always has a charge of -2 because it's in group 6A. These guys do not have equal and opposite charges, so we're going to use crossover. So we need 1 sulfur, but in this case, 2 coppers. And so there are our answers, our correctly written formulas. We have formula subscripts where needed, and the metal comes before the non-metal. An interesting group of ions are what we call polyatomic ions. This is when we have a group of atoms that are held together by chemical bonds that has lost or gained 1 or more electrons. It's important to recognize that polyatomic ions are not molecules, as they have an overall electric charge. There's a fairly small number of polyatomic cations. The two that are going to be most relevant for our class are the ammonium ion and the hydronium ion. There are a lot more polyatomic anions, and many of these contain oxygen and are referred to as oxyanions or oxoanions. Those words mean the same thing. Different folks have a different preference for what term they use, and here's a sample listing of some polyatomic anions. As I mentioned, most polyatomic anions are oxo or oxyanions, in where we have a non-metal bound to 1 or more oxygen atoms. Often a non-metal will form several oxoanions. For example, chlorine forms a family of 4 oxoanions, where we have 1 chlorine with 1 oxygen, 1 chlorine with 2 oxygens, 1 chlorine with 3 oxygens, and 1 chlorine with 4 oxygens. There are some names that can help us, some rules that can help us remember the names when we have a family of oxoanions like this. Firstly, if there are 2 oxoanions in the family, the ion with the most oxygen atoms takes the first syllable of the nonmetal's name and adds the ending ate to it, or 8, and then the ion with the least number of oxygens takes the first syllable of the nonmetal's name and adds the ending "ite" to it. So for example, we have NO3 minus and NO2 minus. So the first syllable of nitrogen is NITR. That's what we call the stem name or the nonmetal root. And then because 3 is bigger than 2, we call NO3 minus the nitrate ion and NO2 minus the nitrite ion. When there are 4 oxoanions in the family, such as is formed by chlorine, then our naming scheme becomes a little bit more complicated because we have to have 4 rules. The ion with the most oxygen atoms begins with per, then we give the nonmetal's root, the first syllable of the atom's name, and we end it with 8. So in this case, the most oxygens is 4. So ClO4 minus would be per chlor 8 ion. The ion with 1 fewer oxygen atoms takes the nonmetal root, then the suffix 8, and then we end it with the word ion. So 1 fewer than 4 would be 3. So ClO3 minus is called the chlor 8 ion. The ion with 2 fewer oxygen atoms takes the nonmetal root and the suffix ite. So 2 less than 4 would be 2. So ClO2 minus is referred to as the chlorite ion. And then finally, the ion with the least number of oxygen atoms has the beginning or prefix hypo, then the nonmetal root, and then finally the ending ite. So this would be, and this is incorrect, isn't it? Hypochlorite ion. So the family of 4, the names from in order of decreasing oxygen content go per X8, X8, Xite, hypo Xite, and X is equal to the non-metal root, which is the first syllable of the non-metal's name. So here's a long big table of formulas for polyatomic ions. We can see our common ammonium cation, and then the rest are anions, and in this case it looks like they are all oxygen containing polyatomic anions. We can see that nitrogen and sulfur form a family of oxoanions with 2 differing amounts of oxygen, and then as pointed out previously, we see chlorine forms a family of 4 oxoanions. In the case of nitrate, the 8 is the ion with the most oxygen, and the ite is the anion with the least oxygen, and then the same holds true for sulfate and sulfite. And we already covered this, but when we have a family of 4, it goes per 8, 8, ite, hypo, ite. Now, you guys will need to memorize this list of 10 polyatomic ions. And so you should know the formulas, including the correct charges, as well as the names with the correct spelling. Sometimes you need more than these 10, and if you need more than what's provided here, then you can just look those up in section 3.3 of your text. There are some peculiarities when we're writing the formula of an ionic compound that contains more than one of a polyatomic ion, and the rule is pretty simple. When this is the case, we put the ion in brackets and then add a subscript indicating how many of that polyatomic ion are present in the compound. So you can see this here. We've got ammonium sulfide as there are 2 ammonium cations, we put the whole formula for the ammonium ion in parentheses and then the 2 as a subscript outside. In this case, we have 2 nitrite anions. Again, to indicate that, we put the formula of nitrite in parentheses and then the subscript outside. In this case, we have 2 phosphate anions. So we put the formula of phosphate in parentheses and then the 2 as a subscript outside. Just keep in mind that the cation is always given first, whether it is monatomic or polyatomic. And when we give the name of the compound, and we'll learn how to name these things soon, we always write the name of the cation followed by the name of the anion. And we obviously don't need to include the word ion when we do that. And then the other thing to recognize is that we don't include formulas, we don't include charges in our formulas when we write the formula of a compound. So don't do stuff like that. Okay. So just reiterating, when you write the formula of an ionic compound that contains more than one of a polyatomic ion, you put that polyatomic ion in brackets before you add the subscript. And just keep in mind, the cation is always written first, whether the cation is monatomic or polyatomic. Okay. So when you're using the crossover to construct the formulas for ionic compounds containing polyatomic ions, make sure you check for charge neutrality in the resultant ionic compound. The charges should add up to 0. So barium, because it's in group 2A, it has a 2+ charge. Nitrate has a 1- charge. So the total negative charge is -2. And the total positive charge is +2. They are equal and opposite, so we know we have written the formula correctly. The other thing that we should always check is that we have the lowest whole number ratio of ions that we can't simplify by dividing through by some factor. So let's have a little bit of practice here. It says write the chemical formula for an ionic compound composed of each pair of ions. So we've got the magnesium ion and the carbonate anion. So there's magnesium, it's in group 2A, and so we know that magnesium has a 2+ charge. The carbonate ion is a polyatomic ion, so we look up its name and formula in a table, and we can see that it has the charge 2-, and its formula is CO3 2-. As these guys have equal and opposite charges, we know that they're going to come together in a 1-to-1 ratio, and we don't need to use the crossover procedure. The aluminum ion is in group 3A, and metals in group 3A have a 3+ charge. So we can go ahead and write the charge for that. The acetate ion is a polyatomic anion, and let's see if we can find it in here. And we see that there's 2 ways that folks write this commonly. They write it as C2H3O2-, or they write it as CH3CO2-, and either is okay. I like to write the first one in this case. And we can see that these guys don't have the same size charge. The aluminum ion has a 3+ charge, whereas the acetate ion has a 1-, so we're going to use crossover. So we need 1 aluminum, but we're going to need 3 acetates. So we put the formula for the acetate anion in parentheses, and then as a subscript, we write 3 outside. And let's just correct something here. That should have been 2, shouldn't it? There we go, C2H3O2-. Okay, so there are our 2 answers, MgCO3, and then aluminum, parentheses, C2H3O2, close the parentheses, 3 as a subscript. So now we're asked to identify each compound as ionic or not ionic. And what we're looking for is, does the formula begin with an anion? So the first formula begins with N2, and there are no polyatomic cations that start with N2. So this means that this must not be ionic. Our second formula starts with Fe, and that's a metal, and metals form cations. So it begins with a cation, it then ends with chlorine, and that's a nonmetal, and nonmetals form anions. So that means that this guy, it's a compound formed between a metal and a nonmetal, it must be ionic. Let's head up here for C. NH4, that's the ammonium cation. PO4, that is the phosphate anion. So we have a cation combining with an anion. It must be ionic. And then finally, SOCl2. So let's look for SO. There's no SO that represents a anion, or a cation, or an anion for that matter. So this must not be ionic. So giveaways that a compound is ionic is that it starts with a metal or NH4. If it starts with either of those things, odds are that it's ionic. In fact, it will be ionic for our purposes. And that concludes the section on formulas of ionic compounds.